Hi all! How much memory does your HPC job need? How can you ensure that your job isn't going to run out of memory while also making sure that you aren't over-allocating nodes and wasting valuable resources? Welcome to this third video in a series on HPC performance based upon the work of Dr. Douglas Pase of Sandia Laboratories. My name is Chris Fry and I'm an engineer with Synergy, maker of the HPC Performance Tool Survey. In the previous video, we introduced Survey and the 7 questions every HPC user should ask before running a job. In this video, we're going to focus on the first and most fundamental question: how much memory does my job need? Getting memory right is critical. Underestimate and your job crashes with an out-of-memory error. Overestimate and you may be requesting more compute nodes than you really need and potentially waiting longer in the queue. Let's look at how to get it right. Out-of-memory errors are one of the most common reasons jobs fail on HPC clusters. When a rank tries to allocate more memory than is available, the Linux kernel out-of-memory killer terminates it and usually takes your whole job down with it. The frustrating part is that these failures often happen late in the run after you've already burned hours of compute time. Understanding your memory requirements upfront saves you from that pain. Avoiding out-of-memory errors requires 3 things. First, knowing how much physical memory your job will need. Second, knowing how much physical memory your compute nodes have available. And third, allocating enough nodes that the total node memory exceeds your job's requirements. You may also find it useful to know the number of cores per node, since that determines how many ranks you can run per node. Let's look at each of these. Estimating memory from scratch is tricky. Here's why. Memory requirements grow and shrink as a simulation develops. You might start small and grow as the problem evolves, or spike during certain operations like remeshing. Memory that is freed by your application may not be returned to the system until the process terminates. So even if you free memory, your process footprint might not shrink. Your job is limited by the maximum memory needed, not the average. If you spike to 8 gigabytes once during a 10-hour run, you'll need nodes that can handle 8 gigabytes, even if you're at 2 gigabytes the rest of the time. The Linux kernel shares memory for program binaries, which is good. It saves you memory when running multiple ranks of the same executable. But the kernel, daemons, and other system processes also use some of your node's memory. You don't get 100% of what's installed. Given all this complexity, the best approach is to extrapolate memory use from measurements of similar problems. The relevant measurement is the physical memory high-water mark called maxrss. Different ranks will use different amounts of memory, so to be safe, estimate total memory use based on the rank with the largest maxrss value. Survey gives you everything you need in one place. Let's look at the output. First, the summary header tells you about the hardware. This tells you the processor type, how many nodes you used, the number of processor sockets, the number of cores per socket, and the hardware threads per core. It also gives you the estimated memory available on the node. Then the Analyst report summarizes your job's memory usage. Usage max is the high-water mark for the most memory-hungry rank. This is the maxrss value you need for planning. Usage average is the average peak across all ranks. When these values are close, your memory usage is balanced across ranks. When the usage max is significantly higher than the usage average, you have imbalanced ranks and your maximum is your constraint. Estimated avail is the estimated memory available per rank. This value is obtained by looking at the memory available on the first compute node just before the run and dividing by the number of ranks on the node. The percentage column shows you how much of available memory you're using. In this example, the job is barely touching available memory at 0.09%. If this percentage is low like this and you are using multiple compute nodes, you may be able to decrease the number of nodes you are using, at least from the point of view of memory usage. If this percentage is high, you may want to increase the amount of memory available to the job by adding more nodes onto the run and thus more memory. With this single report, you have all the data on your job's memory that you need. Memory usage per rank, available node memory, a quick comparison of usage to available memory, and cores per node. Sometimes you don't just want to know how much memory your job used, you want to know when it was used and whether you're at risk of running out. Survey has an optional memory timeline feature that helps diagnose out-of-memory conditions. To enable it, just add the -- memory timeline flag when running Survey. By default, Survey samples memory every 5 seconds. If you want finer granularity, use -- memory sample interval to specify the seconds between measurements. This samples every second, which is useful for short jobs or when you need to pinpoint exactly when memory spikes occur. Let's look at what the memory timeline shows you. Here's output from a job that ran into trouble. Right away you can see warning signs. The peak memory was nearly 63 gigabytes on rank 1. Memory grew by over 259,000% during the run. It started small and ballooned. And critically, system available memory dropped to just 186 megabytes, only 0.1% of total. That's a system on the edge of running out. Survey then detects the likely out-of-memory condition. That jump in available memory at the end, that's the kernel's out-of-memory killer terminating processes and freeing their memory. The memory timeline also shows you the peak memory for each rank and when it occurred. All 4 ranks peaked at about 63 gigabytes each. On a node with 234 gigabytes total, 4 ranks at 63 gigabytes each, we need about 252 gigabytes, more than what was available. No wonder the out-of-memory killer stepped in. Survey also tells you which ranks disappeared before the job ended. These ranks were killed by the out-of-memory killer partway through the run. Rank 3 went first, then rank 1, and then rank 0. Survey also outputs an HTML and a PDF report. These more visual reports include a graph of the memory over time when the memory timeline is enabled. The top plot shows the MRSS for each rank. You can watch memory climb as the simulation progresses. The bottom plot shows the system available memory dropping towards 0. When you see available memory approaching the critical threshold, you know you're in danger. In this example, you can see exactly when memory pressure became critical and when ranks started dying. The memory timeline isn't just for diagnosing failures, it's also useful for understanding your job's memory behavior. Does memory grow steadily or spike at certain phases? The growth rate metric tells you how fast the memory is climbing. Do all ranks use similar memory or is one rank much larger? The per process peak table shows you the distribution. How much headroom do you have before hitting the limit? Watch the system available memory over time. If you see memory growing throughout the run, your job might need more memory for longer simulations. Or if your job has different memory requirements for different phases, you could maximize your resources by dividing the job up, creating additional checkpoints, and allocating different numbers of node for the different phases of the job instead of just making one large allocation for the entire job. If you don't have access to the Survey Performance tool, or if you want to check a cluster before running a job, there are other ways to get memory available on a node. Run the free command on a compute node and look for available. This gives you the estimated memory available for the job, not including all the memory already in use by the Linux kernel and other required system applications. Be sure to run this on a compute node, not a login node. Login nodes may have different memory configurations. You can also get similar values from lsmem, NUMA control -- hardware, or just cat/proc/memory info. You won't be able to determine how much memory the application actually uses without some sort of performance tool, such as Survey. Similarly, if you need core counts without Survey, run the lscpu command on a compute node and look for cores per socket and sockets. Total cores per node is cores per socket times by the number of sockets. In this example, 24 cores times 2 sockets equals 48 cores per compute node. You can also get similar values from NUMA control -- hardware or cat/proc/cpu info. Survey gives you the percentage of available memory that your job is using per rank. But what if you want to try adjusting the number of ranks per node? This requires a little bit of arithmetic. Take your usage max per rank and multiply by the desired ranks per node and make sure it fits within available node memory. Let's say survey shows usage max of 4 gigabytes, and say you're planning to run 56 ranks per node on a system with 256 gigabyte nodes. Call it 240 gigabytes available after accounting for the OS. 4 times 56 equals 224 gigabytes. This fits within the 240 gigabytes, so you're fine. But what if you tried 64 ranks per node? 4 gigabytes times 64 gigabytes equals 256 gigabytes. The entire node memory with nothing left for the OS. You're at serious risk of out-of-memory errors. Let's walk through a real-world example, migrating a job from one cluster to another. Let's say you have access to 2 different HPC computer clusters, Cluster A and Cluster B. Cluster A has 192 gigabytes of memory and 36 cores per node. This means it has 5 gigabytes per core, allowing for some space for the OS and other system applications. Cluster B has 256 gigabytes of memory and 112 cores per node. That's about 2 gigabytes per core. Suppose you already successfully ran a job on Cluster A and now want to run a similar job on Cluster B. The Cluster A job is MPI only, takes 4 hours to complete on 10 nodes, and survey shows it uses 4 gigabytes per rank. To ensure you don't run out of memory on Cluster B, your job must meet 2 criteria. First, the total memory used by the job per node must be less than the total available memory on the compute node. Second, the memory used by each MPI rank must not exceed the amount of memory available per core. So let's calculate. On Cluster A, 10 nodes times 36 cores per node equals 360 cores, meaning 360 ranks. 4 gigabytes per rank times 360 ranks equals 1,440 gigabytes total memory used by the job. On Cluster B, 1,440 gigabytes divided by 224 gigabytes per node equals 6.4 nodes. Round up to 7 nodes. 7 nodes times 112 cores per node equals 784 cores or 784 ranks. 1,440 gigabytes divided by 784 ranks equals 1.8 gigabytes per rank. That's under the 2 gigabytes per core available on Cluster B. You're safe. So this job that runs on 10 Cluster A nodes needs at least 7 nodes to run on Cluster B. And what about runtime? Cluster B cores are a little faster than Cluster A cores, but let's assume similar speed. You're going from 360 ranks to 784 ranks. That's a 2.2 times increase in parallelism. With perfect scaling, the job will finish in under 2 hours instead of 4, but scaling is rarely perfect, so let's assume similar runtime until you have experience at the new scale. Memory is the foundation of job planning. You need to know 3 things when planning your job: how much memory your job needs, how much memory your nodes have available, and whether you've allocated enough nodes. Survey's Analyst report gives you all of this in one place: memory usage per rank, node specifications, and available memory. If you need to check a new cluster before running, commands like lsmem and lscpu give you the node specifications. Make sure you are running these commands on the compute nodes and not the login node. In the next video, we'll look at CPU affinity, how compute nodes are organized, what NUMA domains are, and why memory locality matters for performance. If you like this video, please give it a thumbs up and subscribe to our channel. You can also turn on notifications to get notified when we have a new video available. Thanks so much for your time, and we'll see you next time.